Okay, so in this video, we're going to take a look at another example related to the DC machine. This one is a bit more involved than the previous one that we looked at, and in that one we kind of just laid the foundation of how to determine a magnetization curve, and in this case we're going to use the same curve, so the same statistics here, or the measurements, if you want to call them, calculations. This is from the previous example, and if you haven't seen that, I'll link that in the description below so you can take a look. But what we're doing in this video is we're using this information and we're going to understand how we can generate the references for IA and IF, and then a sort of numerical example of that. So I guess it's like a two-part example really, so we'll have two different things going on, and it's a fairly, I don't want to say fairly lengthy, but there's a fair bit of work to be done here. So why don't we jump right into it? The first thing we need to do is we need to get our ratings of whatever rated conditions we're going to work with. So we have that IF, the rated IF, it says is 2 amps. And maybe we should go through and read the question, I guess. A DC motor has the following ratings. So there's 20 horsepower, 150 volts, 1500 RPM, RA equals 0.22, and the rated, that's why it's subscript B, is 2 amps. So if that's 2 amps, chances are we'll be dealing with this set of parameters right there. Okay? And so IF, we say, is 2 amps, or IFB if you want to call it. IFB is 2 amps, which implies that K phi B, the rated flux constant, is going to be 0.788 volt seconds. And where did I get that from? I got that from this table here. Okay? And again, this was calculated in a previous example, and I'll link that in the description below if you're curious as to where these numbers come from. So the next thing we can do is we can find the rated speed. So the rated speed, NB, let's call it, is given as 1500 RPM. This is given to us in the question. Now, what is that in terms of angular velocity? Because we always work in angular velocity. So to convert to angular velocity, you just divide this by 9.55, and that gives you 157.1 radians per second. And then the rated back EMF, let's say, would be with K phi B times omega B, and this is 0.788 times 1.5, sorry, not 1.5, it's 157.1. 157.1 radians, well, I don't need to put the units there. 157.1, and that is equal to approximately 124 volts. So these are your rated conditions of your motor. So what we can do is, as we did in the previous case, we said that we would force the reference for K phi to have a characteristic that has the this is the base back EMF divided by the base speed. And again, if you don't know where this is coming from, I'll link that below where we described the torque and speed control of the DC machine. And in the case where it's greater than the base speed, which you can say is, this is 124 divided by omega m. And so this is when omega m is less than or equal to omega b, and this is when omega m is greater than or equal to omega b. And this can be translated into the following characteristic for the field current, and that's 124 divided by omega b, in this case is again 157.1 times kf, and this is where the kf from the previous part comes in handy, because you can approximate this as being a linear relationship so long as you maintain that your motor current is within the linear region of the magnetization curve. If it's not, then you can't use this value of kf anymore. And here you have 124 over omega m kf, and so this is for omega m less than omega b, and this is for omega m greater than omega b. And so, like I said, in the previous example, we found that kf for this case is 0.39394 henries. And that means we can say that IF star is, it'll be 2 when omega m is less than or equal to omega b. Well, why don't we write the numbers since we're going numerical with everything. 157.1, and it'll be 314.2 over omega m when omega m is greater than or equal to 157.1. So this is what you have now. Now the question asks, how do you generate omega m and, how do you generate references for IF and IA? We've seen how to do it before in a previous video where we just defined these things, but it'll be something like this. So you'll have, let's say in a block diagram format, you'll have something that enters a block and you'll have something that leaves. Now what is this something that enters? This will be omega m, and the thing that leaves is IF star. Now how do you generate this IF star? You generate the IF star by, basically you want to program this characteristic into whatever you're using to generate or to carry out this control. And you want to, this should be a sort of 1 over x type of drop. But you want to have that programmed in there. And this base speed here is 157.1. This region here is governed by 314.1 divided by omega m. And this here is 2. So you want to program this. And that's how you generate IF star from omega m. And then how do you generate IA star? So IA star, you remember, is essentially the way we control the torque. So here we'll have 2 blocks because we have another condition, I guess, sort of to satisfy. But you have, on this side you'll have TM star, and then on this side you'll have IA star. Okay, now here you're going to have, in this block, I should say, in this block, this is going to be, essentially you have omega b divided by the rated back EMF divided by EB. So this is omega m divided by EB. Sorry, I had a bit of a slip up there, brain fart, but it happens to all of us. That's okay. So this is omega b over EB. This can also be 1 over k phi, right? Because you can generate that in that way as well. So this can also be, I guess you can say this is 1 over k phi b. The two are interchangeable. You can use either one. Now what's this? This is the limiter. So this is the limiter, or sometimes it's called the saturation block. So this is just used to make sure that your armature current will never exceed its maximum rating so you don't burn your machine, because sometimes the controller might act to increase the armature current so as to increase this torque reference, and we'll see that later on in this example, that the reference torque that you're trying to provide is not achievable under the set of conditions, and so the only way you could do so is by increasing the armature current, but increasing the armature current will result in a higher current, obviously, through the machine, and it may burn the machine or damage the machine in some other way. So what's next? What's next is we'll look at the rated armature current. So what's the rated armature current? We're going to take the torque, Tm sub b, is equal to Pm sub b divided by omega b. And this is 20 horsepower. To convert 20 horsepower into watts, you say this is 746. That's the conversion factor. Omega b we said is 157.1. And this is approximately 95 Newton meters. So this is the rated torque. So this is the rated torque, meaning this is a machine property. This has nothing to do with what we're doing. This is a property of the machine if we want to operate under these conditions. If we want a base speed of 157.1 radians per second and the machine operates at 20 horsepower, or it has a 20 horsepower rating, then the rated torque that it can provide is 95 Newton meters. The reason I'm emphasizing this is because we come across a number of different torques, and we have to be able to distinguish between what they mean. So, for instance, here we have a reference, here we have a rated, and then next we'll have an actual, what the actual one is, and the three might not be the same. And in most cases they're not the same because they mean different things. So, given that you have your rated torque, you know that, let's say, IF equals 2 amps, and that means K phi equals 0.788. Again, this is from our table at the top. And this means that IA is K phi, well, let's not jump ahead yet. let's say then we have Tm equals K phi IA. And so then you can use this to determine what IA or TMB, let's say these are all B. So these are all rated values because you want to find what the rated current is in this case. So IA B is equal to 95 divided by 0.788, and that's 120.5 amps. And so this is your rated IA. Okay, that means we can kind of check if we're on the right track. And it's always important to check if you're on the right track because it gives you confirmation if what you're doing is correct and if your understanding is correct. So if you have the rated armature current, you would expect it to produce the rated armature voltage. Of course, I mean, that's the definition of ratings. So why don't we check? Let's do a little check here. So check. We're going to say, we know that VA equals IA RA plus K phi omega M. Now, if you plug in all your rated values, you should get the rated voltage. So rated, I mean, there's no rated resistance, but there is a resistance. The rated current is 120.5. The rated K phi flux constant is 0.788. And the rated speed is 157.1. And if you calculate this, you'll get this is approximately 150.3 volts, which is approximately 150, which is given to us in the question as the rated armature voltage, meaning we're on the right track. Doesn't mean we're correct on everything, but we're doing something right, and that's usually some form of assurance is better than no assurance, I suppose. And then we can say if Tm star is 85 Newton meters, we can move on to the second part now. So we're transitioning from the first part into the second part. If you give a reference of 85 Newton meters, which is what they're asking, then what you can do is you can say that this rated torque will have a reference, I should say, not rated, it's reference. Star is a reference. Will require some reference flux and will require some reference armature current. You can obviously calculate this based on what? Based on the equations that we have. So you have IA star, and the reference in this case is 85. And remember, this K phi, we're using these expressions here, right? So all of these relationships that we have here, essentially this is what we're using. This block is what we're using in the form of an equation. And so we would say for this, the denominator in this case is 124 divided by 157.1, which is EB over omega B, or if you want to take it the other way, 1 over KF. And this is 107.9 amps. So this is below our rated, so we're okay for now. And again, you don't want to be over your rated value because that would mean you're doing something wrong. So we're still, these things are still making sense. And so now the question is, what is on the other side? What's happening on the other side of the machine? So you have a torque condition, and then you have the speed condition. So the speed condition requires that omega M is equal to 2500 divided by 9.55, because we do everything in radians per second. So this is 261.8 radians per second. And this implies that omega M is greater than or equal to, well, it's not equal to, I guess. It's not a condition. We're telling you what it is. It's not a check. It's greater than omega V. And this means that you have to be in the constant power region of operation. You can't be in the constant force region. So you have to apply these characteristics. You can't say that it's just 2. It has to be this for IF star. Okay, so let's see what happens then. So IF star is then equal to 314.2 divided by 261.8, and that's 1.2 amps, which also makes sense because remember the characteristic decreases the field current as the speed increases, and this is below 2 amps, so that's again also making sense. So what this means is you should set IF star to 1.2 amps in order to meet this condition. But what we're trying to do at the same time is we're trying to set the torque to be 85, meaning IA should be set to 107.9. Okay, so these are these two sort of conditions that we have. But now what we want to see is we want to see what's actually happening. Because it's one thing to set a reference, but it's another thing to actually see how your system behaves or responds to that reference. So let's take a look at what happens in this case. So if K phi equals KF IF, and you know what KF is equal to, you know this is 394, and you know IF is 1.2 amps, that's the IF star, right, that we just calculated above. That's what we're going to set the reference to. So I guess this should technically be star. And so 1.2 times 0.394 gives you 0.473 volt seconds. That means this is the new, I guess you can call this a reference for K phi as well. And what that means is you've decreased the flux. Now, if you go back to the ideas that we proposed in the speed and torque control videos, you'll notice that we had this thing called field weakening, where we decreased the flux to increase the speed beyond certain values, I guess you can say. That's exactly what we're seeing here. So now you've decreased the flux from what it was initially. So initially we said that the rated conditions, K phi, according to that, was 0.788 at 2 amps. But now, because you want to go to a higher speed than the initial speed that you have, you'll have to, or the speed that this was calculated for, which was 1500, you'll have to decrease the flux, which is what's happening here. So K phi is now smaller than it was previously in order to increase the speed. Now, if you decrease the flux, constant, I guess, or if you decrease the flux and then therefore decreasing the flux constant, you also expect then the torque will also be affected. Why? Because the torque is equal to K phi IA. Now IA we calculated before. We said the reference we're going to give it is 107.9. Now the problem is we've decreased the flux. So K phi is now equal to 0.473 times 107.9 is the torque. Or that's the current, and this gives you the torque, I should say. And this is not 81 anymore. This is now going to be 51 Newton meters. And so you might be wondering what's happening here, because we said we wanted to set this to 85. But that was assuming that you have this reference. You don't actually in reality have this value. So this value is not true anymore because this is under a certain condition. Now what you've done is, in this case, you've said, I want to increase the speed beyond where it was when I did all these calculations and so on. And so therefore you have to weaken the field weakening region. And to do that, you end up also losing out on the torque that you're capable of supplying. So these are sort of trade-offs and such. And so if you remember, I guess another thing we can comment on before we move on is, you remember I mentioned the importance of this limiter here. So suppose you put 85 here, but you've weakened the field to maintain a speed, then this torque decreases, but in order to compensate for that, you might increase the torque here, and the current might try to increase here. But you might get to a point where you start to exceed, where did we calculate that? Here. You might get to a point where you start to exceed this current 120.5. So that's the importance of this limiter here, because you don't want to burn your machine. These are all sort of practical notes, I guess, that we should be aware of, whether you're doing a simulation or a real-life experiment. So the next thing we can check is the power. So the power is Tm times omega m, and that's 51 times 261.8, and that gives you 18 horsepower approximately. So again, we're below our rated power, which is always a good thing. You don't want to exceed the amount of power that your machine can provide, because chances are you've done something wrong, and either your calculation's wrong, or you're in a situation where your machine will not be able to sustain that condition. And I guess one of the last things we can do is we can determine VA, just for the sake of checking where we're at, the same way we just did previously. And this would be 0.22 times 107.9 plus 0.473 times 261.8. And that gives you 147.6 volts, which is below the rated voltage as well. So that's all right. Now, one thing we can try to look at, I guess, to understand, to better visualize what it is that's happening. So let's look at our characteristic. So let's look at this characteristic that we've had, that we're so familiar with at this point. And I'm only concerned with the torque. And so the torque will look something like this. This is Tm, this is omega m. And here we can say we have the base. Here we can say we have the base, and the base we said for this question was 157.1, and this maximum torque reference that we gave here was 85, right? But when we have a certain operating point, which is, let's say somewhere like this, as we're operating at our operating point of 2500 revolutions per minute, in other words, it was 261.8, you have to decrease this. Again, you have to follow this characteristic, right? So it makes sense then that you can't exceed your reference. 85 is the highest you can go. But then you might be wondering, what's the rated machine? Or the machine rating, what does that have to do with anything? The machine rating has to do with the fact that your machine is capable of outputting a maximum of 95. But you're actually only going to use 85. So then I guess one other thing that we might want to do is look at this concept that we introduced of this x theta m, which we refer to kind of like a throttle or an accelerator, or stepping down on the accelerator. It's the way that we control the torque output. So in this case, it's whatever, I mean, in any case, whatever case we had, we always said it was whatever you have divided by the rated, right? So it's your reference divided by the rated. So the reference is 85 and the rated is 95. And this is 89.4%, I guess, or let's say let's not jump ahead there. Let's say it's 0.894. Now this means that we're using 89.4% of the rated IA, armature current, because the armature current and the torque are directly proportional, right? So this is kind of what we have here. We have a situation where in trying to achieve a certain goal of a certain speed, we have to compromise on something. You can't have full torque and full speed. You have to trade off somewhere. So that's kind of the nature of motors, and that's what makes them so interesting, I guess. So why don't we recap everything what we did here? What did we do? We had this table from the previous example, and again, I'll link that in the description if you haven't seen that already. Based on this and these ratings, we determined the rated conditions of the machine that we're dealing with. Based on these rated conditions, we were able to determine what the control scheme would look like. Again, this control scheme is based on the speed and torque control videos where we established these block diagrams and such. And all of these are based on the torque speed characteristic that we would like to impose on vehicles in order to use them more effectively. Based on these characteristics, as well as what's given in the question, we determined what our rated torque is. Rated torque gave us the rated current, and then we kind of just did a little bit of a check. This was like a side step just to make sure we're doing everything okay. And then we calculated based on these references, what the machine characteristics or the motor characteristics would be. And we found that in order to maintain this speed, you had to reduce, or you would have a reduced torque, since K phi is directly related to speed control, but also impacts the torque. So the two are not independent, although we like to use them to control two different variables. So we usually use K phi to control the speed, or I guess K phi is used in the context of speed control, and then IA is used directly for Tm, the torque, because K phi is already a byproduct of IF. And then we kind of just did some other extra calculations to make sure everything makes sense. And then we have this kind of plot. So I guess this is the thing to take away from all of this, to summarize the results. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.